on the next slide. Okay. B-doubles vehicles shown on this slide. Additional consideration should be given to the motorcycles, although they are unlikely to impact significantly on intersection layouts and road geometry. The functional layout based on characteristics of a design vehicle should represent an economic level of design that caters safely and comfortably for at least 85% of vehicles operating in accordance with normal traffic regulations. Larger vehicles, let's say 33 meters B-triples and 30 meters Super B-doubles, and those operating under the restricted access conditions may also be catered for, but this will usually involve encroaching into the other traffic lanes. This may cause some inconvenience to other road users, but may be acceptable because of the floor frequency of occurrence, together with the fact of special conditions associated with the permit. The geometric design should be checked for B-doubles and special vehicles at the areas where problems are most likely to occur. The next design input is speed. For geometric design purposes, it is usual to select a design speed. It is a maximum speed that can safely be maintained over a specified section of the major urban roads when conditions are such that the design features of the road govern. Research conducted in Australia found that on horizontal curves with design speed less than 90 kilometers per hour, vehicles tend to drive faster than the design speed. As a result of this finding, the operating speed concept was introduced. For cars, the geometric design of major urban roads should be based on operating speed 10 kilometers above the legal speed. The operating speed for trucks can be estimated from the relationship shown on the next slide. And now you can see, okay? So if the car traveling with 110 kilometers per hour, in the same common traffic flow, the truck will travel with 100 kilometers per hour, and so on. Where you've got cars traveling with 80 kilometers per hour, it is intended that the trucks will be traveling with 70 kilometers per hour. It's quite interesting to observe design speed versus operating speed. Design speed, as already mentioned, is the speed adopted for the design of each element of the road. The current application of the design speed approach is to select a design speed based on the functional classifications of the roadway that is consistent with the topography and land use and driver is likely to expect, and a speed the driver is likely to expect. Using this design speed, the design varies for geometric elements of the roadway are selected. The designer is given some latitude in selection of the design values of the geometric elements. However, there is no quantifiable methods to examine how the selection of a different design values impact the resulted vehicle operating speed on the road facility. The term operating speed is the 85th percentile speed of cars at a time when the traffic volumes are low. The term 85th percentile indicates that 85ths of car drivers will travel slower than this speed, and 15% will travel faster. In effect, this means that designs based on an 85th percentile speed will cater for the majority of drivers. The 15% of drivers who exceed this speed are generally aware of the increased risk they are taking and they can expect to maintain a higher level of alertness, effectively reducing their reaction times. Desirably, the 85th percentile operating speed should be used for design. There is a noticeable disparity between design and operating speed. Results indicated that horizontal curves with a design speed less than 80 kilometers per hour had 85th percentile speed that were consistently faster than the design speed, whereas the curves with a design speed greater than 90 kilometers per hour had 85th percentile speed that were consistently slower than the design speed. The observed relationship between the design and operating speed is shown on the next slide. Now you can see the comparison. These findings prompted a revision of the Australian design procedure for lower design speed roadways, noting that all of these studies have concentrated on high-speed rural roads. Similar studies have not been conducted on the major urban roads to determine if the same relationship exists between vehicles' operating speed and the horizontal curves. So, the geometric design of major urban roads based on design vehicle car should be based on operating speed 10 kilometers above the legal speed. Side distance. A principal aim of road design is to ensure that drivers is able to see any possible road hazards in sufficient time to take actions to avoid misshape. To provide a calculable parameter that can be related to the geometry of the road, the concept of side distance is used. This concept is based on a number of assumptions. The hazard is assumed to be an object of sufficient size to cause the driver to take evasive action, intruding into the driver's field of view. Specific values are assumed for the driver's reaction time and the dimensions determining the geometry of the sight line. Normally, selection of the extreme values for every element is not appropriate, as the probability of all factors occurring together is extremely low, and the resulted design would become impractical. The assumed parameter values lead to side distances that produce a satisfactory design. Where possible, the side distance provided should be greater than the values recommended in any guidelines. Adequate side distance is essential for safety and efficient traffic operation. The designer should consider the lengths of vertical curves and horizontal and a radius of horizontal curves and the terrain on the inside of horizontal curves in providing adequate side distance. So what are the parameters of the side distance? When determining side distance, assumptions must be made about the following elements: object height, driver's eye height, and driver's reaction time. Side distance is measured between the driver's eyes and an object or pavement marking on the road ahead, as shown on this slide. Object height. The object height to be used in calculation of side distances is a compromise between the length of side distance and the cost of construction. Stopping is generally in response to another vehicle or larger hazards in the road. To recognize a vehicle as a hazard at night, a line of sight at the headlights or tail lights would be necessary. Larger objects would be visible sooner and provide longer stopping distance. To perceive a very small hazard, such as a surface defect or zero object height, would need to be necessary. However, at the required stopping side distance for high speeds, small pavement variations and small objects, especially at night, may be not visible to the most of drivers. Thus, most drivers traveling at a high speeds would have difficulty in stopping before reaching such a small object. A length of vertical curve required at crest increases significantly as the object height approaching zero and the general figure adopted, which provides satisfactory design, is between 0.2 meters and 0.6 meters. Lower object heights can be used at the intersections or road sections to prevent flooding and standing water, and also at locations where there is a high probability of rocks and other debris being on the road. The driver will most likely attempt to make evasive actions rather than to stop for small objects on the roadway. The geometric design of major urban roads, the object height shown on the next slide is recommended. Okay, I believe I said 0.6 meters for the car tail light. That figure has been adjusted recently to 0.8 meters as shown on this slide. Driver's eye height is a combination of the height of driver's stature and driver's seat height. Based upon recent research and considerations of the characteristics of the vehicle's fleet and the aging drivers, the car driver's height, okay, has been adopted as a 1.1 meters, and that's height that should be used for the geometric design of major urban roads. For commercial vehicles, for general geometric design, a driver's eye height of 1.8 meters should be used. For checking distances, for checking side distances on a seg vertical curve, a driver's eye height of 0.24 meters is to be used. Reaction time.